Hi everyone, I'm Stan from OnlyDust, and my mission today will be to try to explain you how the Starks work as if I was explaining it to my grandma. So I'll try to make it understandable. There are a lot of mathematical assumptions I will make. There are some stuff that are oversimplified, but I hope at the end of the talk you will get a rough overview of how Starks work. So let's get going. So my grandma loves to cook, so we'll be explaining it today as a recipe to understand how the Starks work. So we will be making this delicious recipe, which is low-degree polynomial extension with a bit of fried constraints because it's better with this. It looks like a chachuca, so it's really good. And by the end of the talk, you will be able to cook it yourself at home with a bit of ingredients. So what are those ingredients? First one is a problem to solve. So we'll see in a minute what it is and what it means to solve a problem. We'll have to get a form of arithmetization of the problem, and we'll see in another minute what it means. You will need a bit of notions about how polynomials work, basic knowledge of polynomial mathematics and logic. Maybe it will taste better if you add a bit of knowledge about finite fields, especially with finite primes fields. So basically, it's some set of integers that are bounded by a big number. And the last ingredient is kind of reminder on polynomials, which is that when x0 is a root of a polynomial f, then you can write f in a special form. And this is really important because we'll use it like a lot during the talk. So that's a big ingredient you must have. You cannot replace it with some tofu, for example. So first step, find a problem to solve. You can find any problem you want. Here I took the Sudoku problem, which is very basic problem, but it's a good example of how we can prove some program that testify that you have a solution to a given Sudoku. So what we will be proving today is that given Sudoku grid, I know a solution and I want to prove it to someone without revealing what the solution is. The use cases for this are a bit shady, but this is an example. So, the step 2 is to create an arithmetization of the problem, and so to create some math around what a Sudoku is. So what we'll start to do is to represent the grid in mathematical terms. So we'll do basically just a sequence of numbers, which are the numbers of the grid, labeled from x0 to x80. Then we will try to represent what are the constraints of a Sudoku. So for a Sudoku, it's pretty simple. All the numbers have to be between 1 and 9. All the lines have to be valid of the columns and all the small squares. And we'll be representing only the 2 first constraints because the other one are either more complicated or not relevant for the recipe, which will be already very good with the first 2 constraints. So how can we represent that all x numbers are between 1 and 9? Well, you just make the product of the difference with all the numbers between 1 and 9, and you expect it to be equal to 0, so which means that x is either equal to one of the numbers. This is the simple one. Then we need to arithmetize the constraint of lines are valid. And this one is a bit more complicated, but still understandable. a line is valid if all the numbers are different and the 9 numbers take the 9 values of 1 to 9 in any given order. So when you make the sum, it equals to 0, which means that all the sum arguments are equal to 0, which means that, for example, in the case of xi, it's either equal to 1, 2, etc., and so on. You get the point. I hope. So now it's time to make the sauce for the recipe. The sauce today will be the low-degree extension sauce. This is where we can consider that the actual Stark protocol starts. And let's see what this barbaric term means. So we start to choose a special value g. So g is like an element of the finite field, but it's you can consider it's, I don't know, maybe 5. Let's say it's 5. And you associate all the powers of g to the values we have in the Sudoku corresponding to the index. So g to the power of 0 corresponds to x0, etc. And so you have this set of xy coordinates. And once you have this set of points, you plot it and you try to interpolate the point with a polynomial, which I did with my hand and my mouse. So it's not perfect, but this is what a polynomial would look like, taking all the values of the point you've put on the graph. There are a lot of techniques to interpolate a polynomial. Main one is the Lagrange polynomials, but whatever, it's not important for the recipe. The main point is that you find this function f that describes the interpolation of all the points. And then, in the next step, you add a lot of points where you calculate the f values, but these points are not related to the Sudoku. These are some, I would say, random points that you take and you evaluate them on all the f polynomial, and so you end up with having maybe 10 times more points that you had in the Sudoku, but you know that they are all on the polynomial. Once you have this, you commit to these points. This part is a bit tricky. Committing to points is like saying, I want to prove to someone that I know all these values without revealing what they are. And so what I do basically is that I hash them and I communicate on the hash. And I hash them on such a way that the person I want to convince I know the values can ask me for specific values, and with the hash I provided, they can indeed verify that the values I gave is indeed part of the hash computation. And for this, we use what we call Merkel trees. So this is pretty simple. You have all the values at the bottom, and then you hash them 2 by 2. And then you take these hashes and you hash them 2 by 2, etc., until the root. And you communicate the root to the one you want to prove that you know the values. And if you want to cheat, if you modify any value at the bottom, then the root will change. And moreover, if you want to prove that, for example, you know A2 and you communicate on A2, you provide the path of all the other hashes next to A2 up to the root, and the person you're trying to convince can compute themselves these specific hashes and see that in the end they get the same root. And so you convince them that you know these values. And this is a way of proving that you know those values. So you do this with all the points you computed on F, and you commit the root and you send it to arithmetization we did of the problem into a set of constraints that are equivalent, which means that if the constraints are validated, then the initial solution is valid. So for example, for the first rule we had, which was all the values are from 1 to 9, we take it and we transform it with the polynomial f that we computed at the previous steps. So these two writings are equivalent. And then, because of the second line, this says that the values g to the power of I are roots of this polynomial that we have on the right. And if you remember from the introduction, if j to the power of I is a root of this polynomial, then we can write this polynomial in the following form, which is x minus j to the power of 0 times x to... And this is the first constraint we have. This is the process of transformation between a simple arithmetization into a constraint. And we'll see how we can prove that P0 is a polynomial in a moment. Then once you have all these constraints, so here we did it for the first rule of the Sudoku, but we have to do it for the second, for the lines are valid and the columns are valid, etc. You need to combine them in order to have only one constraint. So how we do it, for example, let's say we have 3 constraints. What you do is that you choose 3 random numbers that you ask for the verifiers, for example. You tell the verifier, well, just give me random numbers that you want me to use. And then you combine the polynomials this way, and proving that P0, P1, and P2 are polynomials becomes equivalent to proving that the composition is a polynomial. And this is way simple, because in the end you have only to prove that one constraint is a polynomial, which is way better. And what you do is that you repeat the evaluation that you did for f, for example, but now you evaluate for CP, and you commit, which is that you compute the Merkel tree and descend the root, etc. Then, what do? You take your frying pan in order to prove that CP is a polynomial. We're getting close to the end of the protocol. So how does this work? The fry protocol is a specific part of the Starks, and it's here because of this fact, is that proving that CP is a polynomial is very hard, generally speaking, but proving that it's close to a polynomial of low degree is way simpler. So close is a bit like subjective, but you can consider, for example, that close means that they differ in only, I would say, 2% of the values over the whole domain, by 2, so a slower degree. A lower, sorry. And so how do you do this? Well, once again, you ask the verifier for a random value, and then you separate f between the odd exponents and the even exponents. And this gives you 2 sub-polynomials, g and h, which are of degree half of f. And then you can combine these g and h polynomials with the random values that you got from the verifier and have a new polynomial which is deducted from the first one, but which has a way lower degree, half of f's one. And then you evaluate this new polynomial, you compute the Merkel tree, and you send, once again, the Merkel root. And what you do is that you repeat these steps, dividing d by 2 at every step, until you have a very low value of d, let's say 2 or 1, where g and h becomes constants. They are not polynomials anymore. Well, the specific type of polynomial which are constants. And then you can just communicate these constants to the verifier. and you just committed a commitment. Then you have the commitment at every 5 steps. So you can have many steps. Well, basically you have log d steps, d being the degrees of the constraint polynomial. And you have the final values after the Fry protocol, which are constants. Whoops. So that was for the recipe of building Starks. If you want to go further with this and understand how, for example, the verifier actually verifies the proof, you can read these amazing resources. So what we did here is that we constructed the proof, and I did a lot of shortcuts to ensure you that doing this actually proves that you know the solution to the Sudoku. But the verifying part, and this is where the Starks are brilliant, is not that complicated. It's just like requesting for random values and checking that all the polynomials are still valid on specific points. Well, thank you.